Good morning and welcome to this webcast. Thank you for joining us for another STEMnet webcast. I'm your host, Jennifer Wicks, coming to you from Learning and Development. Thank you for joining us for applications in artificial intelligence and machine learning. Very excited to support the STEMnet team and bring you this webcast. So we will have captions, starting in just a few moments. We look forward to your questions and engagement in the chat pod throughout the entire session today. And we will have the Q&A at the very end, so please do stand by for that as well. And with that, I'd like to go ahead and introduce our moderator for today, Dr. Frank A. Gomez. He is the Executive Director of STEMnet at the Office of the Chancellor. And with that, I'll hand it over to you, Dr. Gomez, to get started.
Jennifer, thank you for the kind introduction, and welcome to all of you to another STEMnet webcast. I hope you and your families are all healthy and safe today. Today's webcast is another exciting one focused on artificial intelligence, machine learning, AI, ML. Humans are increasingly coming into contact with AI and ML systems. At times it is evident, as in the case of Siri, Alexa, Cortana, or Google Assistant. It is also evident in the case of self-driving cars or non-player characters in computer games. At times it is less evident, as in the case of algorithms that work behind the scenes to recommend products and approve bank loans. It is easy to see how AI is altering our world and raising important questions for society, the economy, and governance. Given the potential for intelligent systems to impact our lives, it is important to design intelligent systems with this in mind. While intelligent machines are unlikely to unseat humans in the near future, they will come into their own as a valuable tool. Because of developments in neural technology and data collection, as well as increased computing power, AI will augment and streamline many human activities. It gives me great pleasure to bring together a sampling of CSU faculty conducting research in the area of AI and ML to speak on their work and to provide us a primer on what some feel is ushering in another industrial revolution. Whereas a previous industrial revolution harnessed physical and mechanical strength, this new revolution will harness mental and cognitive ability. Before we begin, I want to remind the audience to use the open chat box on their screens to type in their questions. Our speakers, when not presenting, will make every effort to respond in real time. So let's begin and hear about some of the exciting work happening in our CSU. Our first speaker is Ilmi Yoon from San Francisco State. Ilmi, the floor is yours.
Thank you very much, Frank. Good morning, everyone. I'm very honored to be part of this webcast today. The title of my talk is Machine Learning Enhanced Video Accessibility for Visually Impaired Users. I have been very fortunate to work with wonderful collaborators and amazing students over a few years. And I'm sorry that I can't read all of their names and contributions due to the limited time. And we all know that video has become an essential part of entertainment, education, and even for social connections. Because of this importance of video, that it could potentially create a new digital divide for the visually impaired users who are hundreds of millions worldwide. To reduce the gap, one possible solution is using audio description. It is the narration added to the soundtrack to describe important visual details. udescribe.org was founded by Dr. Josh Milley, one of my collaborators, to be able to ask sighted volunteers to come and describe videos from the wish list. There are more than 3,000 volunteers who have been describing the video. So here I like to show a video how udescribe works right now. And due to the overlap of the echoes, I'm not going to talk, but you will be hearing that the sighted volunteer is describing the text on screen or what is on the scene, the visual details.
English appears in the center. New South Wales Education Standards Authority and their curriculum on varying languages. However, there remains a lack of facilitation. The English hello is replaced by Auslan's fingerspelling, and the Spanish and Thai greetings are replaced by the Auslan greeting for hello and hello in Braille, respectively. Towards language and communication in the disabled community, including the deaf community.
Can I go back to my slide? Due to the limited time, I will pause the video, but I guess you get the idea. And please visit youdescribe.org to see wonderful audio descriptions. Audio description presents a solution for this problem. However, it still has many challenges. First of all, producing audio description is difficult. Deciding what to describe creates a huge cognitive load, and it takes time and many tedious tasks. Most of all, volunteers cannot catch up to the speed of video production. From the recent YouTube statistics, 300 hours of video are uploaded in every minute, and almost 5 billion videos are watched on YouTube every day. Looking at YouDescribe itself, about 93% of wishlist videos are not described yet. These are the difficult challenges, and we like to take advantage of AI and machine learning to address these challenges. So the machine learning, especially image caption generation, does a very impressive work that from the input images, it encodes and then it decode into the natural language sentences. In this example, from the input image of giraffe to the giraffes standing, and it is advancing year by year. So we started with baseline description. That baseline description is the one you saw in the previous example, that it automatically reads out with the soundtrack, and it have a summary of visual contents. It also reads out the text on screen. They are played either as extended or inline. Extended is the one that you saw which paused the video because there was no sufficient gap to read out, and if there are gaps, inline is preferred. We developed the AI system which supports that started with a scene segmentation. When there are major scene transition happens, we break down into the scenes, and we also read out we pick the best keyframes and to be able to read out the text on screen, and also keyframes for the image caption generations, and then we produce to the sighted volunteer for revisions. So these are the interfaces. As you can see, here is a scene 1, here is a scene 2. So here are the texts from the image caption generation. And if there are text on screen, it will be displayed here too. And when the sighted volunteer revised this text, they can click on this text on speech. Then it will produce this page with all these audio files that are already converted to text, to speech. And the white are the only gaps in this video. So it used the yellow as inline description, and these red bars are the extended description which pause the video. The sighted volunteer can listen and make some changes to it. With this, interfaces, we recruited 22 sighted volunteers and asked them to describe one video with AI-supported system and one video without AI-supported system. And we measured their time, and we did interview with them. And as you can see in the results, that AI-supported system was highly preferred and was much quicker. With this, that we also recruited 12 visually impaired users and asked them to listen and rate those videos. And we were happy to find that the AI-supported audio descriptions were statistically significantly better, and which means that it produced higher quality audio descriptions. We also developed to the next level, which is on-demand description. Baseline description reads out and there is no control, but on-demand description, we want to give the control to the blind users who can control when and what, so they can decide when they want to hear and what they want to hear. As you can see here, that from the images, that you can ask a question: do you think the woman is with him? And we can provide an answer like, no, I don't think so. So this is the based on the technology visual dialogue, and one of the collaborator, the Abhishek Das, has this key technology. Starting from there, that we are applying to the video. And we also use the D key and Q key. So some people like to just the description rather than asking question. So there are two ways of working with it. So we call this as infobot. And now I'm going to play a video which will show that how it works. While we are working on this new user study, we wanted to produce different conditions. And one of the condition is using 100% AI baseline description, because as I mentioned, 93% of video are not described yet, and it is important to test what AI can do as a baseline description. So the video I'm playing will have the baseline description with the male voices, which are explaining the baseline description, and also there are female voice, which is reading the text on screen. And there you will hear some of my questions and answers.
Pain.
Where's that? Yeah, just look at my
A person holding a cell phone in their hand.
up a little bit.
Lay down, baby, lay down.
We created a makeshift gurney and Milo was cooperative.
Okay, there we go. He's like,
It's okay.
he's gonna lie down.
He knew we were there to help him.
It's okay.
Oh.
There we go. Okay. It's okay. Just you can lay everyone down in the bed. Just be careful with your faces.
A close-up of a woman in a car.
This is here. Okay, so yours is not too bad. Milo.
How's Milo doing?
Taking selfie.
What color is Milo?
White.
Is Milo healthy now?
Yes. A close-up of a dog laying on a bed.
After getting pain meds, antibiotics and a bath, Milo started feeling better.
Milo.
A close-up of a dog laying on a bed. A small dog is holding a dog in its mouth. A woman is using a laptop computer in a room. A close-up of a person with a dog.
The recovery process was long, but Milo is a trooper and he is now happy to receive a
That is sitting on a couch. A dog laying on the floor next to a person.
How many dogs?
2.
What color are they?
Black.
What color is the second dog?
Brown.
because of your support.
Can I go back to my slide? That you could see that AI is making some mistakes, like taking selfie or not accurate sometimes, but it shows that how it works with the current AI technology. We recently did a pilot test with 4 blind users, and they are very excited to see the potential of this technology. And we are planning to launch new user study to about 30 to 40 blind users during December. That we have been creating multiple conditions that will be measuring that the on-demand, the infobot only, or the infobot with AI baseline description, or infobot with a human baseline description, or only infobot as multiple combinations. The next step is that we like to increase the quality. We like to integrate the current UDescribe X into the public UDescribe website, and we like to also increase the accuracy of the image caption generation. And during the process, we are collecting data from the cited volunteers who are revising the captions. We add this to the existing YouDescribe data, which have a very good visual descriptions. And there are questions, answers. We are collecting data. We plan to compile all this data and the open source data set to improve the machine learning models. Most of all, this data could potentially generate very specifically for visual impaired users. And I like to acknowledge that the Ability Center and CSU AWS credit that we funded our project. And these are our papers working on this project. And now because of my class, I cannot stay until the Q&A later today. And if you have a question, please send me an email at ilmi@sfsu.edu. Now I'll be presenting Professor Mohammad Pourhomayoun from Cal State LA.
Thank you, Ilmi. Good morning, everyone. I hope you're all healthy and safe. My name is Mohammad Pourhomayoun, Assistant Professor of Computer Science and the Director of Artificial Intelligence and Data Science Research Lab at Cal State LA. And today I'm going to talk about some of our AI projects with main focus on healthcare applications. Maybe 1 or 2 decades ago, artificial intelligence was something only in science fiction movies, but these days we have AI everywhere in our life and we use it every day. There are many different applications, of course, for that: online shopping, social media, internet, speech recognition, and so on. But I'm going to focus on one of the most important applications, which is healthcare. And it's my favorite field of research. I'm going to talk about 3 of our main projects that we are working on in my research lab. So the first project is using artificial intelligence to address COVID-19. So this is a project that we have started back in March. It was the COVID-19 was at very early stage at the United States at that time, but at the same time, many hospitals in European countries were really overwhelmed with patients, with too many patients. They didn't have even time the doctors even didn't have time to visit the patients. So we started thinking about developing an AI algorithm that can help decision making, that can help doctors. And at that time, the data was very limited. We developed a predictive model based on artificial intelligence and machine learning to determine the health risk and predict the mortality risk of patients with COVID-19. Of course, the model can be really helpful to help hospitals and medical facilities decide who needs to get attention first and who has higher priority to be hospitalized. So our first model was developed based on the data of 17,000 patients only because the data was limited at that time. And then by time we collected more data and more data. We retrained our machine learning model several times, and the latest version of the model has been trained based on the data of a couple of million patients. Back in April, we right away made the results of our research public so that it should be available to all other researchers in medRxiv. And after that, we published several papers, conference and journal papers on this research so far. So here is the results, how it looks like. The AI algorithm can predict the patient's mortality risk with more than 90% accuracy, the latest version of the algorithm. Well, it can also extract the most important risk factors, and it's completely data-driven, so it extracted from data. This is how the algorithm works. So this is an example output of the picture on the right. It shows the example output of the algorithm. As you see, well, this is a test results for 15 patients. The first row show the results of the first patient. So for the first patient, the mortality risk is only about 1%. Survival rate is about 99%. For the second patient, the mortality risk is 14%, and the survival rate is, of course, 86%. And these probabilities calculated based on the machine learning algorithms from historical data and based on all of the information that we had from patients, including physiological information, demographics, and other information. So again, for more information, you can review our papers or you can take a look at my website. The second project that I wanted to talk about is artificial intelligence and machine learning for chronic disease monitoring and management and predicting medical conditions. So this is a research that I started about maybe 10 years ago, and I have published more than maybe 40 papers with my students on this topic so far. The main idea is to monitor patients from home. So we provide patients with different type of chronic disease. We provide them with various devices, medical devices such as body sensors and so on, that they can collect their data remotely. Well, the data can be also collected through self-reported questionnaires that the patients can send us on timely basis. And in the back end, there is an artificial intelligence algorithm, an artificial intelligence predictive model in the back end that collect all of those data, and based on this data, it can predict medical conditions. It can predict, for example, it generates alerts if the patients are going to be in bad medical conditions in future, and it can generate warnings, send those information to the doctors, and so on. We applied this system for many different chronic disease in the past couple of years. For example, for cardiovascular disease, diabetes, cancer, AIDS, heart failure, osteoporosis, kidney failure, and liver disease. And the results are really good. As I mentioned, please feel free to take a look at our papers that we have published in this field. I want to show you two of the two cases, and the first one is in diabetes, monitoring patients with diabetes, and this AI model for diabetic patients can predict continuous glucose levels in patients with diabetes based on physiological data we collect them, based on physical activity we can receive from their, for example, Fitbit device, and nutrition information. And the other case study that I want to talk about is the AI, this system that I talked about in cardiovascular disease. So we use machine learning to predict medical adverse events in patients with cardiovascular disease or heart failure. And the algorithm can predict medically adverse events such as heart attack or emergency cases or hospital readmissions a few days before happening with pretty good accuracy, more than 80% accuracy. So again, there are some papers published in this field that if you are interested, please feel free to see my website. And the third project that I wanted to talk about, this is again another research that we started about 3 years ago with my graduate students at Cal State LA. Artificial intelligence and machine learning for cytopathology for early detection of cancer. And well, it can be applicable for many different types of cancer, many different conditions, but specifically we were working on a case study in cervical cancer. So as you know, pap smear test is an effective method for early detection of cervical cancer. It's very effective, of course, diagnosis method. However, it's very expensive and time consuming because pap smear test method, it requires that the expert trained pathology pathologists visually examine all of thousands of cells in microscope. So when they get a sample, so this is how a sample looks like, the right picture. This is a sample that a pathologist needs to check under microscope. And as you see, there are thousands of cells in this sample, and he or she needs to check these cells to find one abnormal or cancerous or malignant cell. So we developed a machine learning algorithms, an AI model that can get this image, this image as an input. So we used high resolution cameras to scan this image to this microscope sample. This was very high resolution. The size of the image is 300,000 by 100,000 pixels. So the size of each image was about 30 gigabytes. And we developed AI model on big data to detect any cancerous sample, any cancerous cells in this image in a fraction of seconds. And according to our latest results, the accuracy is more than 91% accuracy in detecting different types of abnormalities. So as you see, there are different types of the abnormality. To tell you how difficult the problem is, the first picture on the left, the left picture shows a cancerous cell, but the right one shows a normal cell. So the AI should be able to distinguish between them. And again, we have published several articles and journal papers on this research so far, and we are still working on it to improve the accuracy of our method. So next steps, of course, well, these are some of the projects that I talked about with main focus on healthcare. There are several other applications. There are many other projects that I'm working on in my research lab in collaboration with my graduate students and undergraduate students that we are working together, doing research, publish papers, and so on. And many different other applications, for example, in climate change, air pollution, traffic management. So I believe it's just the beginning. So the next step is for all of us to start thinking about how we can use artificial intelligence and machine learning for social good. How we can use artificial intelligence to make our world a better place for ourselves, for others, and for our children. So these are the 17, well, this is an example. These are the 17 Sustainable Development Goals defined by United Nations. And I believe we can use artificial intelligence to work on these goals and make our world a better place for everyone. So thank you so much for your time. Now, I would like to introduce the next speaker, Dr. Jonathan Ventura from Cal Poly SLO.
Hi, thanks, Mohammad. It's a great message at the end of your talk. So I'm really glad to be here. I'm a professor at Cal Poly San Luis Obispo in the Computer Science and Software Engineering Department. And I'm going to be talking about some of my research in computer vision with deep learning. So I'm going to talk about two different projects that I've been doing recently with students and also faculty here at Cal Poly, including Andrew Fricker in social sciences and other faculty across California, and undergraduate and graduate students here at Cal Poly. So I'm going to talk about two different projects. I kind of work in different areas in computer vision, including 3D vision and applied problems in the sciences. So I'm going to talk about learning to predict depth in panoramic video and counting trees in remote sensing data. So in this first project, the goal is to be able to take an image as input and predict the depth at every pixel as the output, so what we call a depth map. So you can see here on the top we have a panoramic image. It has a 360-degree view of the scene around you. And the goal is to be able to output a depth map, as can be seen here on the bottom. So this is color-coded so that brighter pixels are closer and then darker pixels are farther away. And so this is actually an output of the final neural network. And you can see that it's getting the shape of the trees at sort of a medium distance, the sky is far away, and then the street is close to you. There are some artifacts in the output, as you can see here, that I'll discuss later. But that's the general goal, is to be able to kind of convert an image into a 3D model of the scene around you. That's something that, for example, humans do with your two eyes. You can use stereo vision to do this. Or on self-driving cars, for example, they would have a spinning LiDAR unit on top of the car that uses lasers and measures time of flight to estimate the depth, a dense depth map. So if we can do this in a panoramic image, then you can imagine using this as a replacement for LiDAR on a self-driving car. For example, LiDAR is very power hungry and heavy, and so if we could just put a small panoramic camera instead, it would be a lot lighter and more power efficient to do that same kind of 3D depth sensing. You could also use this, for example, in virtual reality. So if you could take an image and convert it into a 3D model, then you can render new viewpoints, you can interact with the model in a 3D sense. So there'd be a lot of applications for this technology. So the work that we did on this, involving undergraduate students and a graduate student here at Cal Poly, who actually defended his thesis last night, yesterday evening. What we're doing is building upon some recent work in this area that does this in an unsupervised way. So actually, we just take video, just raw video, and we don't actually have ground truth depth maps to regress to. We just take the raw video itself, and from that we can use the neural network to learn how to predict depth. And the way that works is that we actually predict a depth map and also the camera motion itself. So if you have the camera motion and the depth map, then you can reproject one image into another, and then you can use that as a supervision signal. So if you take the difference between the actual image and the reprojected image, you can use the error between those two images as a signal to improve the neural network. So that's how we can learn to predict depth in an unsupervised manner, which is great because it's difficult to get perfectly matched images and depth maps to use for supervised learning. So in this work, we're actually using panoramic images, whereas most work uses just pinhole images with a small field of view. So to do that, there are different representations, but we chose the cylindrical representation, which makes it easy to use in a convolutional neural network. So we don't have the kind of distortions you would have with other panoramic representations. So we had to convert the neural network to use cylindrical coordinates and cylindrical projection, as can be seen here. And we had to modify the padding so that when you filter over their image, when you go over the edge, the right edge of the image, it will actually grab pixels from the left-hand side. And when you go over the left side, it'll grab pixels from the right-hand side to do the padding. So this effectively makes the network aware of the horizontal wrapping aspect of the panoramic images. So here are some results. We tested this on real data as well as synthetic data. And we use synthetic data because it's difficult to get ground truth for real data, as I said. So we used a self-driving car simulator to render panoramic video with perfectly matched panoramic depth maps. So you can see here on the right, there's an input synthetic panorama and the predicted depth map on the bottom. You can see it gets the shape of the buildings and the trees pretty well. There are still some artifacts in the street, which I think is caused by the ambiguity in the textureless regions. But actually, my graduate student was able to improve on this with a better model, so we actually are doing a bit better on the street now. And on the left, you can see some new viewpoints being rendered by actually putting a mesh over the depth map and then just rendering new viewpoints. So this is kind of the virtual reality application. You can imagine putting this in a headset so you can actually move your head around and see the scene from different viewpoints. So in terms of accuracy, we were able to get about 85% of pixels in the synthetic data set were within 2-meter error. So it's nowhere near the kind of accuracy you could get with LiDAR, where you would get really like 2 or 3 centimeter error. But it's probably good enough for getting the general shape of objects and doing this kind of virtual reality rendering. So that's one project in the 3D vision area where I do a lot of work. And I also enjoy collaborating with faculty in other disciplines and looking at problems where we can apply computer vision for interesting problems in the sciences, in biology and geography. And so this collaboration was with faculty members in the UC system and also at Cal Poly. And the goal here is to be able to identify and categorize trees in a forest to the level where we can identify their tree species. So we want to be able to find the trees and identify their tree species all from aerial imagery. So typically, to catalog a forest, you would need to actually walk the forest and write down the different trees that you see and identify them visually, which is a very intensive process. So the idea here is that can we just use remote sensing data and automatically identify all the trees in the forest? It's a very difficult problem because the trees can be very close to each other, and even for a person, it's difficult to identify some of these trees, distinguish them. So if we could do this, then we could automatically catalog forests, identify how many of each species there are and where they are. And this could be useful, for example, in researching biodiversity or studying the effects of climate change or forecasting the effect of a changing climate. So the data we had here is from the NEON project, which collects a huge amount of data in different ecologically interesting sites across the US. We were working in the Sierra Nevada forest, and the team actually walked the forest across several transects with a high accuracy GPS device and marked down the tree species as well as the location. And so we had 8 different species plus a dead tree label. We have 700 trees labeled in the data set. Unfortunately, we have really severe class imbalance. So, for example, the black oak only has 18 examples, whereas others have far more examples. So it's kind of a difficult machine learning problem in that respect. And the data we have is called hyperspectral imagery. So it actually has over 400 channels as opposed to just red, green, blue like a normal image. So it gives us a lot of information that we can use to identify the trees. We used principal components analysis to reduce that down to just 32 channels because that seemed to work better with the neural network. And we compared using a neural network to identify them from just color imagery and the hyperspectral imagery. And with color, it's very difficult to distinguish the trees. We only got a 64.64 F-score, basically a 64% precision and recall here. And with hyperspectral, we got up to 87% precision and recall, so far better with hyperspectral. It was difficult, for example, to distinguish white fur and red fur. That's actually, the scientists told me it's actually difficult visually for them even to distinguish the white fur and red fur. They look very similar. And sometimes it was difficult to distinguish dead trees from the live trees. But overall, we did pretty well with this, and we're excited about this. This was published last year. It's gotten, I think, almost 20 citations now, so we're excited about that work. In the future, for these projects, I'm looking at a lot of different avenues to improve them. In the depth map estimation, we're looking at different loss functions, ways to regularize it to improve those artifacts that you saw. And in the long term, I'm really interested in how we can use deep learning to enable a user to capture an entire scene so you can view it in virtual reality. So we kind of started that with this work, but we're looking at other representations for the scene to make that happen. And for the tree counting, we're looking at adding other data sources such as LiDAR. And we also have a new data set that's really exciting with 5 million trees that we have from a project with CAL FIRE, where we're looking at trees in the urban forest, so that's in cities, and doing the same kind of analysis. So thanks very much for listening, and now I'm very excited to introduce Xiaorong Zhang from San Francisco State University.
Hi, thank you, Jonathan, for the introduction. Good morning, everyone. I'm Xiaorong Zhang, currently an associate professor of computer engineering in the School of Engineering at San Francisco State University. My presentation will discuss the use of machine learning technologies in the development of the next generation neural-machine interfaces for neurorehabilitation. So what is our research? Imagine this scenario. When you feel thirsty, the act of reaching out your hand and grasping a glass of water may be effortless for most of us. But this is not true for the 32 million amputees worldwide whose lives are severely impacted by their limb losses. So most commercial prosthetic arms require the user to switch the control mode, for example, from hand open to make a fist, manually or using body motion, which is cumbersome. I think most of you may know the famous film series Star Wars. The major character Luke Skywalker lost his right hand in a duel with his father. Later, Luke's missing hand was replaced with a prosthetic one. The new hand looks realistic and also functions as if it was Luke's own hand. So the question is that a scene only exists in science fiction movies? Can we control a prosthetic limb as if it is the user's own limb in real life? So, supported by the National Science Foundation Career Award, the goal of my research is to make science fiction a reality. We aim to develop the next generation neural-machine interfaces that allow intuitive and natural control of prosthetic and rehabilitation applications. For example, a prosthetic arm that performs like a natural arm. So what is a neural-machine interface, or NMI? Simply speaking, an NMI is a communication pathway between the human neural control system and machine. It is an interface that utilizes neural activities to control external devices. So the figure in this slide shows a few types of neural signals. The bioelectrical signals collected from the cortex of the brain, peripheral nerves and neurons, and muscles contain a lot of important information that can represent human states, such as emotion, intention, and motion. So the NMI collects the neural signals, decodes these signals using signal processing and machine learning methods, and then controls an external device, such as a prosthetic limb, a robotic system, or a computer application. The hardware and the software of the NMI are usually required to be tightly integrated on embedded computer systems for practical use in real applications. The whole system is also a biomedical cyber-physical system, which features a tight combination of and the coordination between the system's cyber elements and physical elements. So the neural signals collected from muscles are called EMG signals. These are effective bioelectric signals for recording muscle stimulation and expressing movement intent. The EMG signals can be measured as electrical potentials by surface electrode placed on skins. This slide shows a few examples of different EMG sensing systems. These include like single channel sensor measuring a specific muscle or a low-cost armband that has an 8-sensor array measuring muscles around the forearm, and also high-density sensing system that measures hundreds of channels of data using grid electrodes. When performing a movement task, different muscles have different contraction levels. The image on the right shows the EMG signal collected from this low-cost 8-sensor EMG armband by an Android app developed by our team, which is called MyoHMI. So each sensor in this armband is represented by a color block. So when the block is tapped, the EMG signal from that sensor is displayed in real time. So the goal of our NMI is to identify users' intended movement according to the muscle activities, and then make decisions to control the external device, such as automatically switching the control mode of a prosthesis. So to achieve our goal, challenges still exist in both software and hardware design of the NMI. Users with amputations or muscle impairment may not have enough EMG recording sites available for neuromuscular information extraction. So dynamic signal processing strategies are required to extract meaningful neuromuscular information to accurately decode user intent in order to achieve high functionality and the robustness of the control system. The accuracy and reliability of the system can be further complicated by environmental uncertainties such as motion artifacts, sensor contact loss, sensor shift, and fatigue. And for the management of the computational resources, integrating software and hardware on an embedded computer system is usually required and also very challenging. Embedded computer systems are usually resource constrained and operate on batteries. So this NMI implemented on the embedded computer system should be real-time, memory efficient, reliable, robust, and energy efficient. And our research aims to address these challenges mainly from a computer engineering perspective. We have been integrating machine learning-based signal decoding and high-density grid sensing technology and new computing framework and technologies into our research, aiming to develop low-cost, robust, and reliable NMIs for real-time control of neurorehabilitation applications. And this slide shows an example of how machine learning methods are applied to EMG-based NMIs for hand and arm motion recognition. So multi-channel EMG signals collected from the forearm muscles are the system input. In our research, we have used different types of EMG sensing systems for different aspects of our project. And these include low-cost sensor array like the EMG armband, and also high-density EMG system that collects hundreds of channels at the same time. So the raw EMG signals are pre-processed by amplifiers and filters, and then segmented by sliding analysis windows. And after that, the next step is feature extraction. So for each analysis window, features that characterize EMG signals are extracted. The purpose of this step is to reduce the dimension of the input data and also extract meaningful information from the noisy raw signals that could represent the unique patterns of different motions and gestures. The features are then fed into the machine learning or pattern recognition module, which basically enables the NMI to have the intelligence to learn the patterns from the data and make decisions. These decisions are basically the user's intended movements, and which can then be converted into control commands for the external applications. So the bottom images show the implementation of each of these steps: the data collection, pre-processing, feature extraction, and pattern classification in our MyoHMI Android app. This app will be made open to the public by the end of the project period. So one of our research projects is to investigate the effectiveness of high-density sensing technology in EMG-based NMIs. Compared to conventional single-channel-based sensing methods, high-density EMG has the potential to provide richer neuromuscular information from both the temporal and the spatial dimensions. But at the same time, it has higher computational burden and is more prone to variances and disturbances due to its high density and multi-channel characteristics. So we developed a new computationally efficient feature set from the spatial temporal domain, which has been demonstrated to provide higher pattern recognition accuracies for classifying hand and wrist gestures. Another important aspect of our research is to develop neurorehabilitation applications through multidisciplinary collaborations. And this slide shows two example applications. Jennifer, could you help place the video? Thank you. So on the left side is a 3D printed power prosthetic hand controlled by the MyoHMI app and also the 8-sensor EMG armband.
Right.
And on the right side, it is a first-person shooter virtual reality game, also controlled by hand and arm gestures using the app and also the armband and an Oculus VR goggle. So basically, the user can use hand and arm gestures to control the game, like to shoot or to control the setting of the game, turn on, turn off the light, things like that. So this is just 2 examples. This slide shows another example, an application which is called V-Rehab. It's a low-cost mobile VR system featuring multi-channel table tennis game for in-home post-stroke upper limb rehabilitation. And our ongoing efforts and long-term goals include developing new hierarchical computing framework, utilizing new computing technologies such as edge computing and neuromorphic computing to concurrently achieve massive computing power, large storage capacity, real-time response, portability, and connectivity for the next generation NMIs. And also, we've been developing sensor fault tolerance modules and investigating new machine learning methods, including deep learning methods for more robust and reliable high-density EMG-based NMIs. Our group has also been actively collaborating with researchers from different disciplines to develop new applications. And this image shows an ongoing collaborative project with Dr. Quintaro from Mechanical Engineering and Dr. Hughes from Kinesiology and the Health Equity Institute at San Francisco State to develop an in-home robotic therapy system for post-stroke patients. So last but not least, I would like to thank all the student researchers and alumni who contributed to this research, and also our collaborators and funding agencies. So in short, our journey is still ongoing. Both my students and I are excited about this research, and I look forward to receiving feedbacks and suggestions and finding potential collaborations. And we hope one day we could make science fiction a reality. Thank you very much. So next, I would like to introduce our next speaker, Dr. Jongwook from Cal State LA.
Thanks, Xiaorong. Hi, everyone. My name is Jongwook. I want to introduce big data and AI for data analytics and prediction today. We have met the issues of large-scale data last more than 10 years. It has the characteristic of 3B and 4B. Simply, we can say data becomes too big and it grows too quickly. Also, the data format is of non-structured or semi-structured. It means that using the traditional system is really hard to handle that. Actually, we can handle it, but it becomes too expensive. So we can technically say we cannot handle it. Therefore, actually, we need a new system that is not expensive. Also, it provides the service of storage and computing. Therefore, we can define the big data as a non-expensive platform, which is distributed parallel computing systems, and it can store a large-scale data and process it in parallel. Since 2006, the Apache Hadoop and Spark became popular as one of the big data solutions that is actually non-expensive supercomputer, and it is actually available to public than the traditional supercomputer because it is open source. So anyone, any small university lab or small company or small research center, they can own supercomputer that is dedicated for data-intensive computing. So this is architecture of traditional. This is architecture of the big data platform. In the left side, this is the architecture of cloud computing big data services. It has a cluster for storage with multiple storage servers, and also it has a cluster for multiple computing servers, and they are connected through network, and they work together as a single cluster. Virtually it's like a single computer. And another approach is using on-premise servers, using a commodity server such as Linux servers. So Linux server, the single cluster has a multiple Linux servers, and each server has a storage a computing power. And this cluster is composed of 4 or to 20,000 servers. Depends on how big your organization is, and they are connected through network. So both both architecture, technically it is composed of multiple servers, but virtually it is a single server, and we can call it supercomputer, especially for large-scale data set. And around 2015, deep learning, since 2015, deep learning has been popular because Google provide the TensorFlow library with the NVIDIA GPU chip. And GPU chip has like thousands of cores inside to provide the parallel computing. And the famous scholar Andrew Ng has provided this kind of chart to explain that the larger the data set, the higher the accuracy, the higher the performance, especially for neural network, that is actually deep learning. It means that using the traditional machine learning algorithm, when the data becomes large, still the accuracy is kind of flat at a certain point. However, using the large-scale neural network, when the larger the data size, the accuracy, the better the accuracy, the higher the accuracy. So it means that we could use neural network and deep learning to improve our prediction model. However, there is a gap between big data community and deep learning community. If you look at this, there is a big data cluster with multiple servers, and in the left side, there is a deep learning server with a GPU inside. To use large-scale data to build a prediction model in a deep learning server, you actually need to take data from, for example, big data server to deep learning server using network that has a potential bottleneck issues. So in big data community, there was an approach to provide the deep learning library, deep learning service in big data platform. It means that you can use a deep learning library, and you can also leverage a big data platform for data engineering and data analysis as well. And it is called distributed deep learning or scalable deep learning. So we've been using it. We've been adopting those big data and AI platform with multiple collaborators such as City of Los Angeles, LA Zoo, LAFD, with other universities such as USC, Penn State, and also big data companies such as Databricks, Cloudera, Tableau, Neo4j, Elasticsearch. And we received the research and teaching fund from famous cloud computing companies such as AWS, Oracle, Google, and IBM, and collaborate with the companies such as One of Us, SoftGen, and Wider Planet to adopt this big data and AI platform. And one of our projects that we developed is traffic data analysis using Waze traffic data that is greater than 20 gigabyte with the City of Los Angeles. This is actually temporal spatial analysis, means we can see the traffic by time and location, and also we can predict the traffic by time and location. It is we developed it using big data service such as PySpark and Hadoop. Also, we lately developed COVID-19 dashboard to show confirmed and fatality cases, and also we can predict those cases in 3 days. For 3 days. There is another temporal spatial analysis and prediction. And using this, based on this knowledge, we published many papers. One of the paper we received the Outstanding Paper Award in APICIST with the traffic data analysis and prediction. And we also published many papers, many journal papers indexed by SCIE and Scopus, which are famous index. Also, our COVID-19 dashboard was shown at Campus News, recognized by the president and provost. And I was invited to Arirang TV to talk about COVID-19, and also become a faculty mentor honoree. And the lessons learned using this big data AI for machine learning and deep learning is this platform is linearly scalable for larger scale data set. Also, it supports high performance computing. And especially for distributed deep learning, some data set in certain domain works well. However, other domain, the traditional machine learning still works well. And next step I can do is actually I need to adopt various distributed deep learning platform, including media data sets such as video and image and audio. And also, definitely, I need to collaborate with the domain expert in industry for proceed popular fraud detection and ad click, and time series prediction and analysis, and smart things such as smart factory and smart city, and scientific applications such as material science. But you know, I'm an expert in IT, but I need also domain expert to collaborate together for this. And also, I need to deliver and enhance the courses about deep learning and AI based on this collaboration. In summary, I would say, I said the big data is to store and compute larger scale data set based on distributed parallel computing system. And also, I introduced the big data analysis and prediction using Hadoop, Spark, and distributed deep learning. That is for big data science and machine learning and deep learning. And also, we need various domain expert and domain are needed. So this is what I tried to say today. And I want to show you the video that has a traffic data and COVID-19 data by time and location. So yeah, so I just want to share with you how the data analysis looks like based on time and geolocation. And this is the end of my talk. And I want to introduce Professor Kurfess at Cal San Luis Obispo.
Thank you very much, Jongwook. And I'm very honored to be in such illustrious company. And what I would like to talk to you about is my experiences with doing research with very limited support and mainly through class projects. So this is a bit more shallow in comparison with what you've heard before, and also involves collaboration with many other partners. So I'm going to talk about two examples that I've conducted over the last few months and years. And one of them is about the safety assessment of school buildings in collaboration with our Cal Poly DX Hub, the Digital Transformation Hub, and the World Bank that is interested in helping poorer countries make sure that their school buildings are in good shape. So what we're trying to do with that project is make efficient use of the resources at the World Bank. Right now they have to send experts to countries to inspect school buildings and then write reports. And of course that's very time consuming, very expensive, and it cannot really be done at a large scale. So what we're trying to do is taking images taken by local people, instructors, teachers, administrators, parents, maybe students themselves, and use these as the basis to identify the structural types of these buildings and then also try to assess in what shape they are. This is a collaboration with the DX Hub, with the World Bank, and then we also plan to collaborate with one of our exchange partners, the Hochschule in München, the University of Applied Sciences there, but unfortunately our plans there were disrupted by COVID. So we were planning to hand this over to a class taught by my colleague Dr. Socher there, but unfortunately we had to scrap these plans. So this is the first project. The second one is about shark spotting with drones, and here we're collaborating with the CSU Long Beach lab, the shark lab there, who actually took the video images that our students here are analyzing. So the idea here is to take video footage taken with drones, spot sharks there, identify other objects of interest like surfers or swimmers or other sea animals, and then alert lifeguards at the beach to the presence of sharks, but also use these analyzed videos for behavioral research of sharks. So for example, under which circumstances do they approach humans, or how do sharks that occur in groups like leopard sharks behave. So I'm going to first talk about the safety assessment of the school buildings. So this is the collaboration with the World Bank and with other universities. And the idea here is to combine community citizen science by involve the people at the location, the people who depend on these school buildings, and help them take pictures and then use these pictures for an analysis by an artificial intelligence deep learning program first, and then further analysis by human experts at the World Bank. So what one team in a human-computer interaction class did was focus on the data collection aspect. So they developed a mobile app that instructs users how to take images that then can be used for that analysis. And what you can see here are screenshots of the prototypes that they developed. So the users, of course, first have to identify themselves, and then they are presented with a home screen that gives them various options. One of them is to take images. Then the users get a quick tutorial on how to place the camera and the building so that these images are actually suitable for that purpose. Then the AI component, which is not integrated in this prototype yet, will give quick feedback on the suitability of the image and tell the user maybe to get closer or zoom in or adjust the angle at which they are taking the picture. Then it takes the picture. It also incorporates the metadata like the location and other questions that we ask the users, and then sends that to the repository at the World Bank location. Then, okay, so this is the screenshot of the proposed improvements for these images. Then once the metadata are uploaded to the central server, then the AI component will kick in, and this AI component was developed in parallel by another class in the winter quarter of this year. And what they do is they take images, put them into a database, and then apply additional labels and meta information that they acquired from the World Bank and train a machine learning model on this data set. The outcome of this learning approach is a categorization of images according to different categories. So what you see here, for example, is a multi-story building that consists of several components. You can see them lined up here in this diagram, and it also has some structural properties that may lead to deficiencies that you see here. So the model ideally will identify the type of building that we have, and for this particular project the team concentrated on 4 of them, so load-bearing masonry, steel frame, timber frame and reinforced concrete buildings. The World Bank has a taxonomy of 12 different types, and we are currently working on expanding the machine learning to recognize different types of buildings as well. So this is a first shot at an assessment that identifies the structural properties of the building, also other factors like the height of the building and possibly also weak points that can be identified from the images. And then this analysis is used by human experts that will then do the final assessment and, if necessary, deploy experts for further inspection. But many of the buildings are expected to be assessed by remote analysis. So for the current quarter, we have a team that is expanding this work in my artificial intelligence class, and in the spring and summer of the next quarter of the next year, we are planning to resume our collaboration that did not work out last year with the University of Applied Sciences in Munich, and a class directed by Dr. Soher will hopefully be able this time to continue this work and convert it into an actually deployable mobile application. So this will hopefully lead to safer school buildings, and instead of spending a lot of money for experts to travel to remote locations, they will be able to use data collected by the citizens there to assess the school buildings. In my second presentation, I would like to briefly talk about the problem of identifying objects in videos taken by drones, and the example here that you can see are sharks on the top image and servers on the lower image, and you can see that it is quite challenging to identify such objects in video footage for several reasons. One of them is that the drones fly relatively high, so the objects are relatively small. The second one is that the water surface is not always as nice and clear as at the top image. Sometimes there's foam or waves, or the water is a bit muddy, and it's more difficult to identify objects that are not directly at the surface. So for this project we used machine learning, and we used a number of different approaches. The first problem was that we had to label images, and that was a collaboration between the students in my class and then students at the marine at the shark lab at CSU Long Beach. Then once we had the labeled images, we trained a convolutional neural networks to perform image classification, and we got decent results. The results are a little complicated to explain because we're trying to identify the location of the object and also the recognition accuracy. Did they identify the correct object? And the results are a bit lower than what you would expect in similar projects because of the difficulty of recognizing the sharks from aerial images and also in images that have disturbances in them. So this was work that was done in initially in two of my classes. In parallel, my colleague Dr. Maria Pantoja also had a team working on the same problem in a class on deep learning that she taught. Then it was continued as a summer undergraduate research project in the last summer. There are two more teams working on my current class on it, and they all use expertise that is provided by the CSU Long Beach Shark Lab. So the results here was that we are able to recognize and distinguish objects with a reasonable accuracy of about 80 to 90%, and this is the basis for tracking the movements of sharks. So in the remaining time, I would like to talk about the lessons learned. So what I try to do is let the students pick their own topics, and this increases students' motivations. There are rewards of collaboration, but also drawbacks. So students have expanded opportunities. It's the basis for ongoing activities, but to be honest, it's also quite challenging to coordinate all of these activities and hand over the succession of projects and make sure that the collaborations with the external partners work. In summary, for me, it indicates that research at teaching-focused institutions is feasible. External funding is good, but not always critical. So for the projects that I presented to you here, we got a total of about $10,000 of funding for the summer undergraduate research project. But it is also a good basis for taking this to the next level through master's thesis or through funded research that many of my colleagues presented earlier. So this is my presentation, and I would like to hand it over and let Dr. Reza Akavian from San Diego State University continue with his presentation. Thank you very much.
Thank you so much, Franz. Good morning, everyone. My name is Reza Akavian, and I'm an assistant professor of construction engineering in the Department of Civil, Construction, and Environmental Engineering at San Diego State University. Thank you for staying on until this presentation. This is the last presentation in this series. I'm sure that you enjoyed the very informative and interesting talks by my colleagues so far. What I'm going to do is to talk in the general theme of AI applications and continue that discussion with applications and use cases in construction engineering and in the construction industry, but also dive a little deeper into one project that we did with my students in my research lab and talk in more details about that. My research lab is actually called DICE, Data Informed Construction Engineering, and that is the logo of the lab. I put it here because I thought it's a good segue to our discussion. These DICE here that are building blocks of this structure capture the intuition that construction operations, construction processes are replete with uncertainty. So some of the technological advancement like robotics, automation, these little cute drones have helped with alleviating the problems that occur because of this uncertainty. But what really we need is what we resort to essentially is artificial intelligence, because it can work based on historical data and then predict the future. So because of those uncertainties, there are a number of challenges that construction practitioners and researchers all agree about, that these are probably the most important, the grand challenges in construction. We have a very high accident and injury rates in construction, one of the most dangerous industries all over the world and in the United States. Also, we have a very low productivity, a stagnant productivity in construction compared to other industries that are worker-focused and worker-centered, like manufacturing, for example, or agriculture. And then also the shortage of skilled labor and workforce, and then aging workforce, essentially. Now, these problems have been solved to some extent in some applications and in some studies. I'm showing a few different studies, recent studies by colleagues in the US. For example, this is a design automation and optimization framework which automates and optimizes a repetitive design task that is traditionally performed by hand through computer implementation. So imagine a design software which generates an optimal solution which may not be computed using traditional calculation methodologies. Or maybe visual progress monitoring. This is a very popular application these days. I can name off the top of my head 3 startups that are working on this, capturing the construction progress in the job sites using 360-degree cameras, and then comparing it at the end of the day with the plans, and to essentially monitor the progress of the project. Or robotics, obviously. I'm showing 2 images here. One is a Boston Dynamics Spot robot, and the other one is another startup, Dusty Robotics. They are used. This Dusty robotic robot is used for interior layout with robot and total station, but at the same time, there are other applications like having a robot as a safety officer in a construction job site. But what I want to talk a bit more about is the project that we did in our group, and we published this year the results in the Journal of Automation in Construction, which deals with worker equipment activity analysis. I'm going to talk only about equipment activity analysis because of the time limits, but I would be happy to discuss other aspects of this work which relate to worker activity recognition and analysis with anyone interested after the presentation. So again, so the problem is the low productivity that we talked about. In our preliminary research, we noticed that lowest productivity actually occurs during the initial phases of a project, where actually the heavy equipment use is the highest. What are the contributors of those low productivity which are related to construction equipment? So, for example, long or frequent equipment idle times, or other non-value adding activities. These not only contribute to low productivity, but also, as you can tell, result in higher fuel use and greenhouse gas emission. So the solution is essentially, or the solution that we proposed was to use the notion of activity recognition that is traditionally used only for humans. So we have the human activity recognition in different fields such as sports science and exercise sciences. But we wanted to apply this notion and understand the design requirements of a similar application for construction equipment activity analysis and classification. So we used sensors called accelerometers. We all have those in our hands or in our pocket because smartphones are usually equipped with these sensors. And then, as opposed to applying it to human, we wanted to apply it to construction equipment, and also at the same time, we wanted to use a more, let's say, advanced architecture of neural network, deep learning, as opposed to the traditional shallow machine learning models. So here's the general overview of the methodology. So we collect data from construction equipment. I will talk about the specifics of the experiments later, but we collect data using accelerometers. Each activity in an accelerometer in a set of data that we collected using accelerometers have signature activity patterns, and then we manually label those activities, those equipment activities, using the videos that we captured during data collection. Then trained predictive models. I will talk about these models in more detail later again, and then classify future activities based on the data that were not seen before. And the result would be cutting unproductive activity patterns, and hopefully in the future, what we are working on is cutting the related greenhouse gas emission. So again, just to give a brief background to those who may not be very familiar with machine learning, what we are doing here is to train a model with some data and then later on evaluate the predictions on the data that the model hasn't seen before. So again, predicting future with new data. Here you can see that we ran two experiments. In the first one, we observed a vibratory roller performing real landscaping work, again with the sensors attached to its body and articulated parts of the equipment. We collected readings from two 3-axis accelerometers at 100 hertz frequency, and then the equipment was performing its routine activities, and we eventually labeled the activities using these labels that you can see. What you can see in these two compactor activities versus time and excavator activities versus time charts are essentially the possible activities plotted against time for these. We broke down these activities into smaller sub-activities, if you will, to essentially evaluate the performance of machine learning models. In terms of the details of the models, we made use of 3 major kinds of architectures in our model: convolutional neural networks, fully connected, and then recurrent layers. So convolutional neural networks are used to essentially extract spatial patterns and then the recurrent networks that are captured in the second model that you can see, the deep convolutional LSTM, or long short-term memories. These are these are used because we have some time series, or the data that we have are actually time series, so they can capture the time or temporal aspects of the activities. And the reason is that these LSTMs, these recurrent layers, have a feedback loop that allows them to consider previous inputs and previous activations. Here I'm showing the results. In the table, you can see different type of equipment with also different combination of activities. And I'm showing the two models, the results accuracy of two models. One, the baseline convolutional neural network, and also the deep convolutional LSTM. We essentially had decent results, 77.6% for the excavator. And by the way, we did not continue with the baseline model once we see the results for the compactor vibration. And so, yes, the result 77.6 is higher than the state of the art. And just for a comparison for you, the random would be something around 14%. What we also noticed is that there is this various category that we considered, which is a catch-all category. Based on the confusion matrices on the right, we realized that most of the activities are confused with those. So after removing that one, we got into even higher accuracy, around 90%, 91% accuracy. So the ongoing work in this area, we also collected some data using another piece of sensor, portable emission measurement system, or PEMS. As you can see, as we were collecting the accelerometer data, we also collected emission data with the hose that you can see is in the exhaust pipe of this equipment to study emissions activity patterns. So essentially linking the activities or the raw accelerometer data that we collect to the level of emissions and to the level of, and then we can eventually connect that to the level of fuel use of construction equipment in order to have more green construction and in order to reduce the greenhouse gas emission effect of a construction projects and construction processes. Some of the applications that we are working on currently are using AI to promote and facilitate human-robot interaction in construction using the state-of-the-art methodologies such as learning from demonstration or imitation learning. We are also working on determining the drivers of trust, usually using AI or robotics really in construction. So that is another application that we are working on. Monitoring the occupational health and stress of construction workers using wearable sensors is another application, and then enhancing construction work zone safety via automated video and smartphone data analysis. I have open positions for master's and also PhD students. We do have a joint doctoral program with San Diego State, with UCSD, University of California, San Diego. So if you know students who are interested in these areas with civil engineering or computer science background, please refer them to me. And finally, the acknowledgement. I would like to thank my current students as well as the alumni, Carlos Hernandez and Trevor Slayton. The credit of this work goes to these two gentlemen, and then the funding resources for my research. And so with that, I think we are ready for Q&A, and I pass the torch to Frank.
Thanks, Reza, and everybody for their great talks. It's really a pleasure to hear all of you, and certainly a lot of very, very interesting work going on in the CSU. We have some time for Q&A right now, and my first question is to Mohammad. Can AI ML make a more accurate diagnosis than physicians?
Well, the short answer is yes, it is possible. Especially if we want to diagnose from a medical image. So right now we have machine learning algorithms, we have AI algorithms that can detect, for example, a cancerous tumor or different medical conditions from medical images like an MRI image or X-ray, CT scan, or ultrasound image with very, very high accuracy, even more accurate than some doctors. And by the way, AI never gets tired. It doesn't get exhausted and make mistakes because of being tired and so on. And it completely makes sense because it's just learning from data. Okay, AI learns from data. So doctors also learns from data and experience. So in medical schools, they first learn from their medical textbooks, and those medical textbooks are all written based on past experiences from past patients. And after graduation, they will learn more and more and more by experience, by practicing those knowledge. Now think about it. If we provide the data of past data of millions of patients or hundreds of millions of patients in the past to an AI model, to a machine learning model, and let it learn from all of those experiences, it can be more expert. It can be the predictions, the detections, the diagnosis by that system can be more accurate than any doctor. So in the short answer is yes, it's possible.
Great, thanks, Mohammed. Hopefully that could even drive down the costs of healthcare too, huh?
Yeah, of course. This is one of the most important advantages.
Yes, very much. Thank you. The next question is to Daniel. What is the greatest technical challenge? To Jonathan. What's the greatest technical challenge you faced in learning to predict tree species in aerial images?
Yeah, that's a great question. Thanks, Frank. So I think one of the main problems was that we had such little amount of data. Usually for neural networks and for deep learning, you just want as much data as you can get. We only had 700 trees labeled, was clearly far more in the forest. And so, that's kind of a major problem. And we ended up doing extensive cross-validation in order to have like a reasonable evaluation of the how it was doing. So I think that's a really common problem that I always hear from people who want to do deep learning projects is that they just don't have enough data. So you can use extensive data augmentation and warping the images or messing with the colors and all these sorts of different things to try to sort of increase the amount of data you have. But in the end, with that kind of data, you can only do so much. So that was kind of one problem, and especially for problems in the sciences, it's difficult to get the data. The team had to go into the forest and actually walk the forest and label each tree. So it's going to be expensive to get more of that kind of data. The other issue was working with hyperspectral data. As I said, it has 426 bands, and the bands are probably very correlated because it's just really small sampling of the spectrum. So I originally thought that we could just put that right into the neural network and it would figure out for itself how to process it, but it really didn't work at all, which is why we ended up using principal components analysis. But I feel like there's got to be a better answer for how to handle that data. But yeah, it's kind of challenging to work with that kind of data. In the future, I'd really like to see if we can use like semi-supervised learning because there are so many tree examples in the forest. It seems like we should be able to learn from the ones that even aren't labeled maybe in some way. So there's been a lot of progress recently from Google and other researchers who are looking at how can we learn from the unlabeled data in some way because it's so prevalent that you'd have lots of unlabeled data. So I think that's a promising area, but yeah, it's definitely still a challenging problem.
Great, thank you. Thank you for your answer. I think the next question is a good one for Xiaorong. What are the challenges in applying AI and machine learning techniques to prosthesis and rehabilitation applications for use in practice?
Thank you for the question, Frank. So to apply machine learning-based rehabilitation application in practice, this developed system needs to meet requirements in several categories, including like high accuracy, robustness, real-time response, portability, and usability. So it's challenging to meet all these requirements concurrently. For example, there might be new machine learning methods developed which can achieve high accuracy for movement intent recognition, but these algorithms might be too complex to implement on embedded computer systems for real-time control, which requires the system to respond, for example, in 200 milliseconds for prosthesis control. And many machine learning methods require user-specific training to create a model or classifier before the system can be used for daily tasks. And if this training process is too long or not easy to conduct by the user at home, the users wouldn't want to use such systems. And in addition, if the system, for example, a prosthetic hand will be worn by the user for several hours continuously, the system must adapt to changes and disturbances in the sensor recordings over time. And these changes might be caused by many factors like motion artifacts, loose electro contact, electro shift, or fatigue. So this initially trained machine learning model may not work well after a few hours. And if frequent retraining or recalibration is needed, the system will be hard to use in practice. So basically, in order to develop a robust, reliable, and user-friendly application for use in practice, it requires joint efforts from multiple disciplines. While significant progress has been made to address these requirements in all these areas, there are not many commercially available machine learning-based neurorehabilitation applications because it's challenging to just meet all the requirements concurrently.
Great, thank you, Xiaorong. I think we have time for one more question here. Jongwook, how much of a cutting-edge technology gap is there between the university and information technology industry? And how can faculty members and universities reduce this gap so it can help students join the industry?
Yeah, I believe we are like a university is behind more than 3 to 5 years. But the good news is we are not the only one. Other universities are also behind. And in order to reduce the gap, the technology gap, we need to collaborate with the industry. Hopefully, we participate in industrial project to know what is the technology that are popular for industry and for our students as well. Also, what kind of a domain they try to focus on. Then that will be definitely helpful for our students to join industry without any issue. Also, since we need to teach to make our students are attractive in industry, it means that based on the collaboration with the industry, we can strengthen or revise our coursework. That should include definitely lecture for theory and the lab for practice. Then definitely we can catch up with the industry. I mean, there is no way to IT industry, unfortunately, the industry is the way, industry is the thing who lead this technology. So we are always behind, but using this approach, definitely we can catch up with the cutting edge technology.
Great, thank you, Jongwook. And certainly I thank everybody for their presentations. Speaker contact information is provided here, and for more information on any of their presentations, you can contact them directly, which may lead to a collaboration or proposal opportunity. In addition, a link to the webcast will soon be made available on the STEMnet website. Questions submitted during the registration period and not answered during the webcast or on the open chat will soon be made available on the private CSU STEMnet Facebook group page. In addition, we'll be sending you all a feedback survey to all registrants today. Please take a moment to respond because your input is certainly important to us. For information on this webcast, please contact Monica Alacon or myself. The previous webcast can be found on the STEMnet website. I encourage you to register for the final STEMnet webcast this term, CSU Exemplars in Biology, scheduled for December 10th. In addition, on December 3rd, we are highlighting a new program called STEMnet Conversations. The first one is entitled Managing Research, Teaching, and Life in the CSU in the Time of COVID-19. Registration is now open. And finally, a few last words. The election has come and soon will be gone, and this event will be in our rearview mirrors. Still, the ramifications of the past 4 years will reverberate and affect our lives and the world for years to come. Need for better words, this American experiment has been a failure. The actions of Donald Trump and his administration have exacerbated the pandemic that has killed over 250,000 people in the U.S., rolled back environmental and public health regulations, and undermined science and scientific institutions. In addition, Trump's education policies may have lasting effects on where children are educated, how federal funding is allocated, and how education-related civil rights are interpreted and enforced. His peddling of chaos and fear rather than facts has both advanced his political agenda and discredited opponents, as well as devalued public trust in the importance of truth and evidence, which underpins science as well as democracy. Yet today is a new day. Perhaps we can look upon these past 4 years as a science experiment gone bad. And just like we teach our students that even through a failed lab experiment we can learn something, so too must we here. I certainly have learned a bit more just how fragile democracy is. As Winston Churchill once said, at the bottom of all the tributes paid to democracy is the little man walking into the little booth with a little pencil, making a little cross on a little bit of paper. On election day, though, we are all big people with great power to make a huge difference in the lives of many and those who will come after us. While it is apparent by the vote that the country is divided, let us look across the aisle for those commonalities to strengthen our country going forward. And always remember, hope is better than fear, and hope always springs eternal in the CSU. With hope, we can change the world. Be safe and have a great day. And I turn to Jennifer Wicks for a few closing remarks.
Frank, thank you so much for your always poignant remarks to wrap up our session today. I want to thank you and also all of our excellent expert presenters. What an incredible session this was today. I want to remind everyone, of course, this session's coming up, as you had mentioned, Frank, on the left side of the screen, and we do have registration opening soon for our session in February. So you'll see that on the screen as well. And until our next session in December, have a wonderful Thanksgiving. We'll see you all very soon on December 10th. Thanks, everyone. Take care.